Hello, Royals. Let's take a look at lesson 5.1 on angles and primary trig ratios. In Unit 5, we are looking at trig ratios. There is a bit of review of grade 10 and grade 11 trigonometry, but we quickly have to get out of the first quadrant. We are going to do some work without a calculator, and then make use of the sine law and the cosine law in applications. We'll also see some issues with the sine law come up. So at first it should feel familiar, but make sure that we're developing skills that are fluid so that we can change to the new definitions when we need them. So in the past, we usually just looked at angles contained within triangles. We may have had a triangle A, B, C, and we would have had angle A across from side A and angle B across from side B. We can still do that, but we need a more formal definition of angles now. We're going to look at a general case where angles are formed between two lines or arms. If we define these two lines right here, one as an initial arm, like a first arm, followed by a terminal arm, or a final arm, then we can define a direction of rotation. I still need to show a pathway for my rotation like this. Where these two arms meet is called your vertex, or your point of interest there. And there's a couple of angles that can be created. I could have gone through, this is like the minor rotation. I've got the major rotation back here. We know we're not talking about the major rotation because I haven't labeled the major rotation. And then the direction is going to become important as well. So in this case, I'm going from this arm to that arm. That's the direction I would have to go. If I went from this arm to this arm, then this would be the initial arm and that would be the terminal arm. Okay, that rotation right there, we can use uppercase letters. If we called this vertex, say V, we can call it angle V. Or we might just use a Greek letter like theta for it right there. It measures how much of a full rotation you've gone through. You're probably familiar with degree measures. I'll estimate that this is maybe like about 40 degrees. What that actually means is I'm going through 40 360ths of a rotation. It's a weird definition because we decided to separate one full rotation up into 360 pieces, probably based on the number of days in a year, approximation for the number of days in a year. You're likely familiar with a right angle being 90 degrees. So you could look at this and say, I think it might be a little bit smaller than 40 degrees. Actually, looking at it now, it looks pretty close to 45 degrees. Okay. When we start working on an XY plane, we're going to place the vertex at the origin. And the initial arm is going to be along the positive x-axis. Okay. We then consider rotations of the terminal arm around the origin to create the angle theta. This angle is said to be in standard position. So yeah, if I put my Cartesian plane there, there's the x-axis, here's the y-axis. I started on the x-axis, the vertex is at the origin. I rotate for a positive rotation in a counterclockwise direction. The angle 40 degrees right now is in standard position. We have lots of experience with angles that aren't in standard position. I could just draw a rotation of about 40 degrees. I'm not on a Cartesian plane. My vertex isn't at the origin. My initial arm isn't on the positive x-axis, so this is not in standard position. Okay. Let's sketch the angle theta equals 60 degrees in standard position. Quick review here. This means that your vertex is going to be at 0, 0. Your initial arm on the positive x-axis. And the other thing, not mentioned up top, but pretty important for us when we start dealing with negative angles down here, is that just the standard that we follow is that positive rotations are counterclockwise. Sometimes students ask me, why do we go counterclockwise? A sarcastic answer would be, why do clocks go the way that they do? There's actually an answer to that. It's in the northern hemisphere, probably based on the direction that sundial's going. Okay, so sketching in standard position. I am not the best sketcher, so I'm just going to grab a ruler here. I'm going to start with the Cartesian plane. So there's my positive x-axis, here's my positive y-axis, there's the origin. To sketch an angle of 60 degrees in standard position, here's my initial arm. I'm starting from the positive x-axis, which means I'll be labeling that 0 degrees a lot. That's me rotating 0 degrees. All the way around would be a rotation of 360 degrees. And that means that a half rotation is 180 degrees, or a flat angle, a straight angle. A quarter rotation, or a right angle, we label as 90 degrees. That means that 3/4 rotations, I'm counting by 90 degrees, 180 degrees, 270 degrees. Make sure you always put units when you're measuring angles in degrees. It's necessary, even in all of your work, not just in your conclusion. Let's say, always label units. Okay, so yeah, 60 degrees. I mean, I could grab a protractor if I had one. I think we can just eyeball it as it's being about, like 60 degrees is 2/3 of 90 degrees. It also should be the angle that creates an equilateral triangle. So I'll eyeball it at about there. Now, I also must show the pathway that I took and the direction that I took to have full marks here. Okay. Well, this will make more sense when we look at other directions and other angles. So you have to show the path and show the direction. Okay. Oh, there's the convention. As convention, positive angles correspond to counterclockwise rotations. Similarly, negative angles, we'll see some negative angles in this course, they correspond to clockwise rotations. One way that students can build I guess, a memory aid for this is by labeling the quadrants. Most of our work happens up here in the first quadrant. In a lot of courses where both x and y values are positive. Perhaps we're familiar then with the second quadrant being here. This is the third quadrant. Here's the fourth quadrant, quadrant 4. I tend to use Roman numerals when labeling quadrants. Okay, that might help you. If you're familiar with the quadrant numbers, that's the same direction that your angle's going. So let's try some examples. And we're going to have definitions in the future that are going to help us sketch these angles, but let's see how we do without those definitions first. Okay. We'll maybe build the need for them or see the purpose for having them. So in every single one of these cases, I should be starting by sketching my Cartesian plane, my axes. All of these are in standard position, so we're starting from the positive x-axis. This time I'm rotating 120 degrees. That's more than 90 degrees, but less than 180 degrees. Instead of thinking of it as being 30 degrees past 90 degrees, you probably want to think of it as being 60 degrees short of 180 degrees. Measuring to the horizontal makes a little bit more sense. Okay. Let's say we were outside and I saw a balloon up in the air here. I don't think I would tell you, like in this direction, I wouldn't tell you look straight up and then down 30 degrees. I would probably say look up 60 degrees. Angles of elevation are given from the horizontal as well. Okay. There's my terminal arm. Here's my pathway. There's my direction. And that's me labeling the angle. Negative 70 degrees is going to be a clockwise rotation. Now it's we haven't rotated a full right angle yet, as much as say 90 degrees in a negative direction. So we are going to be in the fourth quadrant. You might be thinking, oh yeah, that's about 20 degrees short, but we really don't want to reference the vertical too much. So we show that we've rotated in that direction, that path in that direction, and there's theta being negative 70 degrees. See, there's a big difference between rotating that much in that direction and going all the way around here, and that's why it's so important that we label the direction. Negative 240 degrees, I think we've already seen that terminal arm. think it's going to end up in the same spot or terminate in the same spot, be coterminal with one of these angles that we've already drawn. When you're sketching negative 240 degrees, you're not counting by like 1, 2, 3, 4, 5 like that. You're probably saying, okay, I'm going negative 90 degrees, negative 180 degrees, not quite negative 270 degrees. I am going, I think, 60 degrees past negative 180 degrees, or I'm 30 degrees short of negative 270 degrees. So you might notice if we do this accurately that we're going to end up in the same spot as that arm, but it's a totally different rotation. It has a lot, the terminal arm is the same, but rotating negative 240 degrees is not the same as rotating positive 120 degrees. It just ends in the same spot. Okay. A protractor may help you just sort of visualize the pathway, but there's not too many protractors that will go negative 240 degrees. Again, our definitions on the back here will help us if we're getting a little bit confused about knowing roughly where to draw this. As far as marking goes, we can be pretty forgiving. This terminal arm had better be in the second quadrant. It should be closer to the y-axis than the x-axis. But other than that, we're not really looking for a high level of precision. It's like our sketches versus graphing. You're not grabbing I'm not grabbing a protractor and measuring this when marking a quiz or a test. Okay. All right. Angles that share the same terminal arm are said to be coterminal. So our example on the last page, let me just squeeze it in here. Well, there's two other examples here, though. But when we drew 120 degrees, it ended in the same spot as when we drew negative 240 degrees. There's not really a symbol, a math symbol for coterminal that I know of. Maybe we could invent one, or we could look it up. So just use English. I would say 120 degrees and negative 240 degrees are coterminal. Being coterminal is like a plural definition. I can't say, oh, 120 degrees is a coterminal angle, period. I have to say, like, together, I can say 120 degrees and negative 240 degrees are coterminal. Or I could say 120 degrees is coterminal to negative 240 degrees. Okay. Let's watch here. If we sketch theta 1 and theta 2, instead of using different Greek letters, we just use subscripts. Let's show that these two angles are coterminal. We should probably sketch them in standard position to make sure that they end in the same spot. Otherwise, I wouldn't be able to tell that these are coterminal. So 30 degrees would be about up here. That's like splitting this up into 2/3. That's 30 degrees. 390 degrees is an angle bigger than 360 degrees. So I rotate through 360 degrees and then 30 degrees more, meaning that I terminate at the same spot. Okay. Notice that 30 degrees plus 360 degrees is equal to 390 degrees. It would be absolutely false to say that 120 degrees is equal to negative 240 degrees. That's false. Same thing here. 30 degrees is not equal to 390 degrees. I get why students write that. They want to say, oh, they're very similar. They stop in the same spot. They have the same terminal arm. But this symbol means is equivalent to, right? And if one snowboarder does a trick where they turn 30 degrees and another snowboarder does a trick where they turn 390 degrees, they have not performed the same trick. Let's try a positive and a negative one. 150 degrees is a little bit short of 180 degrees. It's about 30 degrees short. So it's sort of related. This angle right here of 150 degrees is kind of related to this angle here of 30 degrees. We'll say why later. Oh, I forgot to use my subscripts. There's theta 1. Here's theta 2. Those aren't superscripts. It's not an exponent. There's theta 1. Negative 210 degrees. I said 150 degrees was like a little bit short from 180 degrees. It's 30 degrees short. Negative 210 degrees is 30 degrees past a half rotation. And that's how I can tell that they're going to be coterminal just on my sketch. As a quick check here, I suppose, let me illustrate it in a different way. If I took 150 degrees and I subtracted 360 degrees, I get 150 minus 360, negative 210 degrees. And that proves that they're coterminal. Right? And if you want to get a formula for coterminal angles, we need to be kind of fancy about it. Angles coterminal to theta are, you start at theta, and then you add an integer multiple of 360 degrees. So you build a formula for it. It's very much like the equation of a line with an initial value and a constant rate of change here. Okay. If I were, we didn't see an example where it was more than 360 degrees. If I were to take 390 degrees and add 360 degrees, I would receive another coterminal angle. 750 degrees is coterminal with 30 degrees and 390 degrees. So if you ask me to sketch 750 degrees, I'm going 360 degrees and then 720 degrees and then 30 degrees more. That right there is a rotation of 750 degrees. It can get kind of silly if you're drawing the entire rotation around and around and around. It's going to look like a nautilus or a snail shell or something like that. Okay. Coterminal is a pretty important definition. It's pretty easy to remember or hard to forget because coterminal angles share, they cohabitate, I don't know, at the same terminal spot, the same terminal angle. Okay. Now there are more important definitions than coterminal angles, but these angles are actually related to them. Scratch this though, because like the principal angle is a special coterminal angle. The related acute angle is not a coterminal angle. Maybe we just call this special angles. Okay. The principal angle, let's say for some angle theta, is coterminal to theta and between, we'll define it in degree mode, 0 degrees and 360 degrees. Okay. There's two ways of remembering this word. One is usually a principle is the most important topic or feature or person. You can also think of the word principle, which means first. So it either means important or first. So if I had like negative 210 degrees and I draw its terminal arm, its principal angle is going to be an angle coterminal to negative 220 degrees that I hit the first time I rotate from 0 degrees. Okay. 150 degrees is an example of a principal angle. Negative 210 degrees is not a principal angle because it's not between 0 and 360 degrees. We'll get some practice with the examples down below. The other special angle is the related acute angle. Now, some people call this the relative acute angle, but I like related acute angle better. It makes a little bit more sense for me. The related acute angle is going to be the rotation. It ignores direction. Ignoring direction. From an angle's terminal arm to the closest x-axis. Okay. We can kind of separate the x-axis into a positive x-axis and a negative x-axis. Now, we've used this number already today. When I drew 150 degrees, I said, oh, look, we are 30 degrees short of 180 degrees. That's how I drew 150 degrees. I didn't count out 150 degrees. And I didn't want to say, oh, I'm 60 degrees past. No, I said I'm 30 degrees short. That right there is my related acute angle. 30 degrees. To sketch negative 210 degrees, I said, oh, look, I'm 30 degrees past 180 degrees. The related acute angle for coterminal angles is always going to be the same, in this case, 30 degrees. Let's just turn to the back for a sec to get some other review of when we use this. 120 degrees was 60 degrees short of our closest x-axis. That's the related acute angle. 120 degrees is a principal angle. Negative 240 degrees was 60 degrees past negative 180 degrees. That's how I knew that these two angles were coterminal, because they had the same related acute angle in the same quadrant. Notice I'm not labeling a direction for the related acute angle. It's not a standard position angle. It's always going to be positive. There's no such thing as a negative related acute angle. And that throws students a little bit on an example like B. But if you, let me ask you the question and see if you get it right. If I ask you, how far from the x-axis is negative 70 degrees? If you understand the definition, then it's easy to get the answer right. It's just 70 degrees off of the x-axis, right? For any related acute angle, there are actually 4 principal angles. Let's demonstrate off on the side here. If I give you a related acute angle, I'll use a number that doesn't show up here, is 30 degrees. Then you have 4 principal angles, one in each one of the quadrants, that has a related acute angle of 30 degrees. We might be talking about the principal angle with a related acute angle of 30 degrees in the first quadrant. Or we might be talking about the principal angle that has a related acute angle of 30 degrees in the second quadrant. We might be 30 degrees off of the x-axis downwards in the third quadrant. Or we might be short 30 degrees of a full rotation in the fourth quadrant. And that gives us 4 possible principal angles. One of them could be 30 degrees. The other would be 180 degrees minus 30 degrees. 150 degrees. The other might be 30 degrees past 180 degrees. 180 degrees plus 30 degrees is 210 degrees. And the last one is 30 degrees short of 360 degrees. Sorry about the space. Okay. I would not try to memorize formulas for how to find your related acute angle. Just draw a sketch. That was 30 degrees. Here's 150 degrees. Here's 210 degrees. And here is 330 degrees. Okay. We're going to try out 6 examples real quick here. These last ones we're going to try to squeeze up top because I wanted some room for ratios that didn't fit on the lesson. So each one of these is in standard position, and I want to find the principal angle and the related acute angle. First one's a little silly because I draw the angle 40 degrees. That is an angle between 0 and 360 degrees, so my principal angle is 40 degrees. How far off of the closest x-axis am I? My related acute angle is also 40 degrees. This illustrates why you didn't need these definitions in grade 10 when you were just working in the first quadrant. It's a little silly. 160 degrees, however, is in the second quadrant. I am probably thinking about the related acute angle when I sketch it. I notice that 160 degrees is short of 180 degrees. It's 20 degrees short of 180 degrees. So that's how I sketch it. Just imagining it being 20 degrees short. There's 160 degrees. Here's my related acute angle of 20 degrees. Now, 160 degrees is an angle between 0 and 360 degrees, so that is the principal angle as well. Okay. For any angle between 0 and 360 degrees, it is its own principal angle. Negative 100 degrees is maybe the first interesting angle on here. I sketch from standard position, from the positive x-axis, 100 degrees in a clockwise direction. Now, you might be thinking, right, we're just 10 degrees past that negative 90 degrees. That's not a great way of visualizing it, because 10 degrees is not the related acute angle. It's going to take us until 5.2 to explain why it's so important here that 80 degrees be your related acute angle. I have usually expected students to show where their answers come from. Sometimes students have a hard time actually getting the calculation right here. You can just ignore numbers and say that your and say your related acute angle is going to be 180 degrees minus 100 degrees. Okay, don't worry about how to use negative 100 in this question to get the answer. Two ways of getting my principal angle. I might see it as 80 degrees bigger than 180 degrees, so I can do principal angle is 180 degrees plus 80 degrees, and I would get 260 degrees. Or I could take my angle, negative 100 degrees, and add one full rotation to that. And that should give me a coterminal angle. And if that coterminal angle is between 0 and 360 degrees, then I know I have my principal angle. I think we can squeeze these in here. 465 might be calculator time here. I'm going to do 465 degrees before I sketch it, minus 360 degrees. That's bigger than one full rotation. That's going to be 105 degrees. So I'm going to sketch an angle of 105 degrees, and that'll be my principal angle. But I need to make sure that, like I was asked to sketch 465 degrees. Maybe I should have started by going all the way around first so that I wouldn't have forgotten to do that. There's 465 degrees with a principal angle of 105 degrees. My related acute angle, I'm short of 180 degrees. How much? Looks like 75 degrees. I think we're okay with just one more example. You can check this one on your own. Solutions are printed. Negative 500 degrees. Here, let's not forget this one. We're going to go negative 360 degrees. Not a full other rotation, though, because that would be negative 720 degrees. Let's do negative 500 degrees plus 360 degrees. And we get negative 140 degrees. So that means I go 140 degrees more or less, in a negative direction. Now, negative 140 degrees is coterminal to negative 500 degrees, but that's not a principal angle because it's not between 0 and 360 degrees. So I add another 360 to that, and I get my principal angle of 220 degrees. 220 degrees is past 180 degrees. Let's figure out how much past 220 degrees minus 180 degrees is 40 degrees. That's how I sketch it. 40 degrees past the negative x-axis. Okay. Real quick, let's just review our primary trig ratios. I'm not sure that we need them for today's homework, but they come up again later, and now's a decent time to review them. Given triangle ABC, where A is 5 centimeters, B is 4 centimeters, C is 3 centimeters. I didn't mention this was a right-angled triangle, but we might be able to see that that actually creates a Pythagorean triplet. Right-angled triangles will usually be given to you in the future. Let's say there's 3 centimeters, here's 4 centimeters, there's 5 centimeters. That would make, let's see, I made side A, so that's A. B is 4, that's going to be angle B. C is 3, so that's angle C. I'm asked to find the sine of theta, the cosine of theta, and the tangent of theta. So definitions, or properties, in the first quadrant are 4 acute angles. We could use these definitions, that the sine of theta is the ratio of the opposite to the hypotenuse, that the cosine of theta is the ratio of adjacent to the hypotenuse, and that the tangent of theta is the ratio of the opposite to the adjacent. These will have to change when we're outside of the first quadrant. But for this question right here, if angle C is my angle of focus 3 is the side opposite, 4 is the side adjacent, 5 is the hypotenuse. That means that the sine of, let's switch this to C, and then we can save a little bit of space. It's going to be the ratio of 3 centimeters to 5 centimeters. That's just going to be 3/5. Cosine ratio is going to be the ratio of 4 centimeters to 5 centimeters. That's 4/5. Tangent ratio, the ratio of 3 centimeters to 4 centimeters. That's 3/4. Then if I was asked to calculate the angle C to the nearest degree, I could use any one of these ratios. I'm going to stick with the sine ratio. And undo taking the sine of with a sine inverse of on both sides. Students usually don't love showing this step. They usually want to write down C is going to be the inverse sine of. Inverse sine of is like a square root of. It has to show up in front of your argument. And you want to make sure that your calculator is in degree mode. Ask your calculator, what's the inverse sine of bracket 3 divided by 5? This came up in some of our prerequisite work, but it's been a long time since we did that. So I'll say that the angle C is about 37 degrees. Okay. Most of your homework has you just practicing your definitions of principal angles, related acute angles, coterminal angles. Make sure, if you haven't changed it, make sure you're not tackling questions 11 or 13 yet. Okay, we'll get to questions like that in the future. Try it out.